In this video, we're going to be looking at encryption, specifically symmetric encryption, before we look at asymmetric encryption in the next one. So what is encryption? Well, to be honest, I've always struggled as a student and a teacher to come up with a really tight, perfect definition for encryption, because there are lots of sort of edge cases and be really careful with your wording in this topic. So this is my best attempt. Encryption uses an algorithm that scrambles data using a key that produces an unintelligible output that, ideally, only those who have the key can reverse. Now, it doesn't trip off the tongue, that definition, let's be honest, but that hopefully covers all of our key areas, and I've underlined the bits which I think are really important here. So scrambles data, it jumbles it up, it takes your original input and makes it completely seemingly random. Now, it does this using a key, and a key is a number or alphanumeric string that is used to scramble up the data in a unique way. Unintelligible means completely ununderstandable. We can still read the output, but it's not understandable unless you were able to reverse this process. And ideally, we design the encryption algorithm so that only those who have the key are able to reverse it. That's the whole point. Yes, quite convoluted. We have this encryption algorithm. Now, there are loads of different ones, some better than others, often involving quite complicated maths, especially at the more complex end. The encryption algorithm will take in two inputs. It will take in what we call the plain text, and it will take in the key. The plain text is your message you're wanting to scramble up. So it could be any message. This is going to get encrypted so that nobody else can understand it. The key is just something I've chosen to feed into this encryption algorithm. The key is important so that I've got a way to reverse the process. It's also important to make sure that this plain text is encrypted differently each time. I want to keep the key secret so that nobody else is able to coincidentally encrypt it to be the same value. Now, the output of our encryption algorithm is the scrambled data. Something like this, you are able to read. You could read out these characters, but nobody could understand what this means because it is encrypted. And this scrambled version is called ciphertext. Now, this is a two-way street. We're able to go back on ourselves. We're able to reverse this process with a decryption algorithm. So encryption puts it into ciphertext, decryption puts it back into plain text. This will often just be running the steps backwards for the encryption algorithm. It has inputs of ciphertext and the key. If the key is applied correctly, we'll go back to our plain text. If any other key was used to try and decrypt it, like if I try to use 456 instead, I get a random plain text, which obviously isn't equal to what it should have been. So the key is essential both to encrypt and to decrypt. Now, it's possible to decrypt ciphertext without being authorized to, in other words, without having access to the key. And the whole field of cryptography is studying this, and there are lots of reasons why people want to be able to break encryption, for security reasons and also for nefarious reasons as well. There are lots of methods to do this, often very mathematical. One method is to look at the ciphertext and try and spot some patterns. If the algorithm isn't particularly secure, it may produce patterns in the ciphertext. So to give you an example, one approach is called frequency analysis, which looks at the most common characters in ciphertext. The most common character in English is E. So you might look for the most common character in the ciphertext, and it might be something like W. Well, you might then assume W is E and sub it in. You might then try the same with the second most common character and the third most common character. And it's rare that's going to work perfectly, and you need to have quite a long ciphertext to be able to do this. But with some encryption algorithms, that is enough to break it and make it plain text without having access to the key. Another method which could be used to crack a fairly weak encryption algorithm is to brute force it. So brute forcing is trying every possible value of your key. And if the key is quite short, then that won't take very long. We often get around this by just having a much longer key to increase the number of combinations, making it not feasible to check every single one. Now, we've really been talking about symmetric encryption so far. The definition for encryption applies to both symmetric and asymmetric, but the examples I've shown you have been examples of symmetric encryption. And that symmetry comes from the fact that symmetric encryption uses the same key to encrypt and decrypt. Asymmetric uses a different key, and we'll look at that in the next video. Now, why do we encrypt data? Well, we encrypt data to try and prevent attackers from understanding important information. We can encrypt files being stored. We can also encrypt files being transmitted. And the point is, if an attacker stumbles across our file, either on our computer or by intercepting it over a network, they would be able to read it but it would be jumbled up. And if it is strong encryption, they would not be able to understand it because they haven't got access to our secret key. But don't forget that not all encryption is particularly strong. Some encryption can get broken really quite easily. To give you 2 examples just to end, you don't need to know these examples, but I think it's helpful just to give you the context needed to understand this topic. One bad one is called Caesar cipher. One good one is called AES. There are loads of other examples in between these ranges. The Caesar cipher uses a very, very short key. So the key is between 1 and 26. That's tiny. There are only 26 combinations of that key. Very, very easy for a computer to check all of those combinations almost instantly. And what that represents is an alphabet shift. Every letter in the plaintext is shifted by the amount of the key along the alphabet. So if I was to run this with hello and 7, we would get this ciphertext, which to be fair is unintelligible. I don't know what that means. If I saw that on its own, I'd be really confused. So it is effective as encryption, except that we can break it really, really easily by brute forcing the key. And also, there is a clear pattern in our ciphertext. S is there twice because I've got L there twice. It's a clear pattern. The key is being applied also to every character, again giving us a really easy pattern to spot. Whereas AES is what Western countries use for most of our symmetric encryption nowadays. This uses a key which is at least 128 bits long, which doesn't seem that long, but actually when we think about combinations, this is 2 to the power 128 combinations, which is a massive number and incredibly unfeasible to try every combination of that. It would take billions and billions of years potentially to try every combination with the longest key size available. To give you an example with hello as our plaintext again, this key does look quite small still, represented in ASCII, but the combinations are massive to try every single one. This would give us an output like this. There are no clear patterns to this. It's good the fact that the length is different to our original, so I've got no clues as to how long the original is. This is a lot more secure and uses very, very clever maths to be able to do this process and make it essentially impossible to reverse the process unless you had access to the key.